All right, good afternoon, everyone. Let's do a little bit of cleanup first. How is the free-frame project going? Okay, not going? Do you have any general questions I can help you with right now? Yes?
What was the clarification that you gave us on the fracture? You said don't do something.
Let's take a look at that. Okay. So remember that one is due on Friday. Let's take a look at it. Okay. So what I'm telling you here is that I would like 3 validations, one of them optional, okay? The last one. The first 2 are relatively easy, moderate. The third one is difficult. So if you don't do that one, don't worry. But the first 2, you have to do them. The first one is a validation of the fracture width. And basically, you are going to get that by comparing the displacement at the fracture boundary in your model with the analytical equation, where the analytical equation is going to be this one, that tells you that the displacement, well, let me turn it the other direction. The displacement in direction y, that's why it's called uy, is a function of the pressure in the fracture divided the plane strain modulus times the fracture half length squared minus distance from the center of the fracture. And this is valid for points inside the fracture. Okay? And that displacement, for example, if I were to draw it on this side of the fracture, is this displacement. And you're going to get those values also from the numerical simulation. So you compare those 2, it should look like an ellipse. This is an equation of an ellipse, and what you should get from the free-frame software, it's also should also look like an ellipse. That's number 1, inside the fracture. Okay. Second validation I want is outside the fracture. We know that inside the fracture, the stress everywhere in direction perpendicular to the fracture, in this case sigma yy, has to be equal to the pressure, because that's a boundary condition. If you check in your model and if you export for the stress perpendicular to the fracture along this line, it should be the value of pressure, because it's a boundary condition. It's something that you set. What is not set is what is the stress beyond the tip of the fracture. So I want you to tell me what is the stress somewhere over here, somewhere over here, somewhere over here, also in this direction. And for this particular case, this is going to be a tension and is going to fade off with distance as you get further and further away. That equation is this one. And you can compare it also with your solution. So those are the 2 things that I want. If you want to do one additional thing, the third one is to tell me what is the stress from here in this direction also perpendicular to the fracture. But you don't have to do that, okay? So this is 1, this is 2, this is 3. We're going to see that later on, that those stresses are going to also decrease with distance, and that's what defines your stress shadow. Tells you how close fractures can be so they do not interact with each other. You can obtain it numerically. If you want, just plot that numerically, and the analytical solution is going to be a little bit difficult, so you can do that or not. It's up to you. Okay? Any other thing? No? Okay, well, if you need help, just let me know, send me an email, talk to Chajin. Chajin was, unfortunately, he was sick this Monday and Tuesday, so that's why he wasn't around, but I think he should be back tomorrow or on Friday. Okay, let's see. All right, so one more thing that I wanted to clarify, and I wanted to let you know, is that I have good news for you. I have uploaded the midterm from last year, so you know what to expect next week. All right, so just go through the midterm, and you're going to get very similar questions. Not the same, but very similar. So make sure you check it out. Okay, you guys had some question? No?
So I guess remember how I emailed you asking about the analytical equations? I used the ones that were highlighted in yellow.
Yeah.
That they were in yellow for a reason.
Okay.
I did not use the two above, and kind of.
Well, but
WO, and I found the maximum aperture because I cut it in half because we used the half.
So this one, it just tells you that there is tension, so there is no solution. This one, it tells you just at one point what is sigma yy.
Right.
But with this entire thing, you get it as a function of distance.
Okay.
They have the same equation, right?
It's the same thing. It's just a solution for a particular point for this one. And for example, this is the width. This is the solution for displacement at the center of the fracture.
Right. And when
Times
I
2.
yeah, it made sense.
Yes.
Yeah, then you cut it in half.
Yeah.
Okay.
So it's the same thing.
Okay.
Same thing. These ones are just for particular points.
And you want for the full
Yes.
distance.
Correct. Yes. All right. So I was telling you that I would share with you some results about Biot coefficient. So from our previous lecture, we talked about the Biot coefficient and what those pore elastic parameters mean. And we talked about how to measure the Biot coefficient. And here I have some results. This is a set of measurements. It's a summary I made from the orange ones are from the book from Jagger, and the blue ones are parameters that were measured in my lab. And here you have porosity and permeability. The lower the porosity, permeability should be lower, but there is no universal relationship for that. It depends on the pore size rather than on porosity. But if we compare that with the Biot coefficient, also you see that for high porosity sediments, unconsolidated sediments like this sand, like this sandstone, the Biot coefficient tends to be large in the order of 0.9. But when you go into tighter rock, it gets lower and lower. And if you were to compare now Biot coefficient as a function of permeability, you also see that for high permeability rocks, the Biot coefficient tends to be high. And for low permeability, tighter rocks, small pore size, low porosity, the Biot coefficient tends to be lower, and around, for this data set, about 0.6, and it can get lower if your rock is even tighter. Something I wanted to notice here is that, for example, here we have two rocks with quite different Biot coefficients, and this is because we have a difference in these two rocks. So Pecos sandstone, let's just look at Pecos sandstone and Weber sandstone. Do you think there could be any reason why some of these rocks, they have a different Biot coefficient but about the same permeability? Yeah. Mineral composition could be, but these two are sandstone, so probably that's the same mineral composition.
Quick question.
Yeah.
So I think last class you mentioned there are three measurements of correlation. So of the three, which one
Yeah.
are you displaying right now?
Yeah. For this one?
Yeah, for this, for what you are showing us right now, which three measurements are those come from?
These come from the book from Jagger, and he measures them similarly to the third method,
Okay.
but measuring compressibilities. It's slightly different method,
Okay.
but it's similar.
Okay.
Okay, well, the difference that you have into some of these rocks is that also the occluded porosity. Remember that occluded porosity is very important, and that can affect your permeability, your porosity. Here I'm just plotting, for example, total porosity. I'm not discriminating between connected porosity or not. So that makes your permeability vary, that makes your Biot coefficient vary too.
More quartz cement than another?
Probably, yes. All right, and then now our objective is going to be to talk about a problem of depleted pore elasticity, undrained pore elasticity, and then we talk about some of these coefficients, especially the undrained bulk modulus. Okay, so one more thing over here, I just remember that the Biot coefficient many times assume as equal to 1. And when you have very porous rocks and you calculate the stresses, you could be making an error by assuming this equal to 1, and if it's not equal to 1, of about 10%, right? Because the difference is just 10% if it's 0.9 and you assume it equal to 1. But as you go into tighter and tighter rocks, that error increases. So that's something that we would like to get to know, because we could have significant errors by not knowing very well what is the Biot coefficient. Okay, so let's talk now about a problem of drained pore elasticity. If you remember, we said that we have solutions that could be drained or undrained, and we'll start now with a drain problem, assuming that the pore pressure dissipates and it does not cause additional deformations to the solid. All right. So this is going to be a drain problem, and we're going to analyze a case of especially of reservoir depletion. Yep. Yeah, I can do that. All right. Let's say that we have a block, and into that block we have a reservoir. Into that reservoir we drill a wellbore. and then we start to deplete that wellbore. Here we have a cap rock. And our objective is going to be to predict what is going to be the change of stresses with change in pore pressure. All right, so let's start with that. In order to do that, first we need to use our equations of relating stresses to strains. Remember that always, if you want to relate stresses to strains, you need to use effective stress. So we have seen this equation already for quite a bit, that stresses are a function of strain. In this particular case, also, since we're going to use the theory of pore elasticity, we must consider effective stress with the Biot effective stress equal to the total stress minus the Biot coefficient, and we're going to consider isotropic properties. So there is just one Biot coefficient, and this is the law for Biot effective stress. Okay, so let's try to analyze this problem. First of all, in any reservoir, we're going to have an overburden stress, which is going to be a total stress. Let me add here a coordinate system. Let me check if this is right-handed. Yes, it is okay. So the stress, overburden stress, is going to be S33. As we deplete the reservoir at a given rate, what's going to happen with the pressure inside the reservoir? It will go down, right? And what do you think is going to happen with the stresses at the reservoir? So we have a flow rate that goes into here. We have a given pore pressure. What's going to happen with the rock?
The effective stress will go up.
Which one?
The effective stress
But which one?
of the rock.
Which, no, but which, in which direction? So let's imagine that let's isolate a cube here. So remember that this is now a three-dimensional problem, and what we have to answer is the variation of stresses in three directions. So let me ask you the following. Do you think that the overburden stress, which is basically the weight on top of the reservoir, is going to change when you do a depletion? No, right? That's not going to change. Why would it change? Doesn't make any sense. So S33 is going to be a constant. Okay. What about now the strains? If the overburden is constant and you lower the pore pressure, you would expect this rock to deform and to compact in the vertical direction, right? What about in the horizontal direction? Do you think that the rock will compact?
Why would rock compact?
I'm tempted to draw some facilities here. Say again, Jack?
Why would the rock compact in whatever direction?
Because if you're lowering your pore pressure,
Oh, right, yes.
and if your total stress is constant, that means that your effective vertical stress is going to go up. if your effective vertical stress, I forgot to bring my piece of foam, goes up in this direction, then this one has to squeeze in vertical direction. But now the question is in the horizontal direction. What's going to happen in the horizontal direction? Do you think that the rock will deform in horizontal direction? Or it would expand? Okay, so what we have learned, or what we have seen, is that if you apply deformation to a solid in one direction, because of the Poisson effect, it should expand, right? But remember, that's always under either unconfined conditions or constant stress conditions. But this is not unconfined, and this is not constant stress. This is closer to what we have seen, and it is known as a one-dimensional strain condition. And you should think this way. Similar to this block, there is also another block here, and there is another block here. So if you push in direction 3, and all these 3 blocks, they try to expand simultaneously, none of them is going to expand, and they're going to be locked in. And because of that, the strains are going to be 0 in direction 1 and direction 2. These two will be equal to 0, and then we're going to get that this is going to be what we called before the one-dimensional strain condition. We're going to see that there is going to be some sort of Poisson effect, but it's not going to be a strain. All right? All right. So each of these blocks then is going to be, it's not going to change size in horizontal direction, not in direction 2, not in direction 1. It's just going to change size in direction 3. This example reminds me, a friend of mine that was saying that once he went to a party that was so crowded that once he raised his arm, he couldn't lower them anymore. And you know, the rock in the subsurface is like that. There is no space to expand. Everything is locked. And why? Because there is more rock around that. And particularly in this example, we're assuming this is infinitely long in this direction, infinitely long in direction 1. So it's a very packed space. Yes, Jack.
Can you use the same analogy to explain subsidence?
Yes, because it's the same problem. If we have deformation in direction 3, that means that on the ground, on the surface, the ground is going to also deform. And here, you know, I'm not making all the deformation the same, but because the closer you are to the well, the more deformation you're going to have, the lower the pressure is going to be. But it's the same thing. It's the same problem. It has consequences in the reservoir and consequences outside the reservoir. Okay. So with these conditions and this equation, let's see what we get. I'm going to change this slightly, and in order to work with strains, we're going to use the inverse of this matrix, the matrix C. And if I write that, you can do it either way, but I'm just going to do it this way. We know this matrix very well. Epsilon 1, 3 and 2 epsilon 1, 2. And if you remember, here we have the Young modulus, Poisson ratio, and I'm just going to write half of the matrix, 1 over E, 1 over E. These are zeros, and these are shear moduli. There's one more thing we're going to assume, and it's that the shear strains are equal to 0. So all of these are going to be equal to 0. But let's just complete the equation. And what we want to do now is to use this equation, but we're going to update it. If you didn't write the stresses, don't write them, because I'm going to change them right now. We want to update this with our new equation, which is the effective stress. So this one is going to be, instead of sigma, is going to be S11 minus alpha pp S22 minus alpha pp and S33 minus alpha pp. And the shear stresses are the same as the total stresses, so I'm just going to leave them the same. We need to write these equations like this because now our variable is going to be the pore pressure. And that's what, to solve the stresses as a function of the pore pressure. All right, so we said that this one is going to be also 0, that this one is going to be also 0. So let's see what is left, and we'll use those equations in order to predict the stresses. Okay, so I think I have a space over here. First equation is epsilon 11 is equal to 0, and that's equal to, and notice that because epsilon 11 and epsilon 22 are both equal to 0, and because our solid is isotropic, that also means that S11 is going to be equal to S22. It's just because of symmetry. So from this equation, S11 is going to be equal to S22. Let's just call it, in this case, let's see, what are you seeing? Direction 2. Let's call it S22. So the first two parts of this equation are going to be 1 minus Poisson ratio, Young modulus, times S22 minus alpha pp minus this. Basically, this is just the this one times that one plus this one times this one plus this one times this one. And what I get from here is that the ratio of effective stress to total stress to effective horizontal stress to effective vertical stress depends on the Poisson ratio. So let me write what I just said. This is one minus Poisson ratio. I'll move it right now. Just equal to that, where this one is effective stress sigma 22 in horizontal direction, and this one is the effective stress in vertical direction. Same thing that we did before. So I'm just moving this one to the other side, so they are both positive, and then move this one down over here, and that's the result. If you remember, this was what we call the coefficient of lateral effective stress. And for example, for a Poisson ratio equal to 0.25, it's 1/3. It tells you that the effective stress in horizontal direction is 1/3 of the effective vertical stress. All right, but now we want to expand these equations to tell us what is the variation of stress as a function of variation of pore pressure. So what we're going to do is we're going to write now these equations as a function of pore pressure. So I'm going to leave my total stress here on the left side, and I'm going to move my pore pressure into the other side, and I will break those terms in a part of total vertical stress and the other one with pore pressure. And this is going to look like this. So that term over here is this, and when I pass the pore pressure on the other side, notice that there is a coefficient over there. This is going to be equal to, it's going to be plus, so pore pressure alpha 1 minus this times pore pressure, right? I think it's okay. And this one is going to be equal to common factor this thing, and this is going to be 1 minus Poisson ratio, 1 minus 2 Poisson ratio. And now we have an equation that tells us what is the total stress as a function of the total vertical stress. So this is total horizontal stress. This is total vertical stress. And this one is pore pressure. Before, I have insisted that you always measure or write equations in terms of effective stresses, because that's the most meaningful stress that produces strains and that make the rocks fail. It's not total stress, but it's effective stress. However, we cannot measure very easily effective stress. In the field, you measure total stress. For example, total vertical stress, you already know how to measure it, right? How do you measure it? Yes. Well, but in general, yeah, the integral of rho GC, right? Where you get rho from the well logs, the total mass density. And what about pore pressure? Pore pressure in a permeable reservoir, you can measure it more or less well. When it's the rock, it's impermeable, it gets a little bit more complicated. But let me find a paper. I forgot to upload this paper. I was supposed to upload it, and I was taking an exam and I forgot. I am writing upload, sorry. I wanted to write stress. Okay. Okay, give me one more try. There you go. I found it. Okay, so let me come back quickly to this equation. This one we know, easy to measure. This one, we can also measure it. If you're depleting a reservoir, and if sometime you stop producing and you just measure bottom hole pressure, you can measure it too. And this one, what about this one? Can we measure total horizontal stress? No, you can estimate it with Poisson ratio, but I'm telling you now to actually measure it. Can you do that? Any suggestion how we could measure horizontal stress?
Well, you can't measure it.
Yeah, you can get close with breakouts, but that's an indirect measurement. Mini fracs or just plain hydraulic fracture. You make a hydraulic fracture and you analyze the data of pressure as a function of time, and you can measure that. We can measure total horizontal stress. And because of that, it's a lot more useful in this case now to talk in terms of total stress. And you will see in the, I'm going to show you an example here. This is actual data that as you lower the pore pressure in a reservoir, so depletion will go in this direction from high pore pressure to low pore pressure, the horizontal stress is going to decrease. And that's why we have to explain why. The minimum horizontal stress. I'm also assuming when I tell you that we can measure horizontal stress with a hydraulic fracturing test is that we're either in a normal or strike slip regime. Because if it is reverse, then a hydraulic fracture test will measure vertical stress, not horizontal stress. So you have to take that into account. But you can measure horizontal stress. And what the data that you see over here is that as you lower the pore pressure, the horizontal stress goes down. This may be a little bit counterintuitive, okay? But hopefully after we finish this topic, you will see that it makes sense. And let me tell you why it is counterintuitive, because we say that when we lower the pore pressure, we're compacting the rock is taking more stress in vertical direction. This plot tells you that total horizontal stress goes down. But what we're going to try to see right now is what happened with effective horizontal stress. Okay, so let's come back to the equations over here. And what we would like to do now is to calculate what is the variation of total horizontal stress with the variation of pore pressure, which in mathematical terms, that's going to be a partial derivative. Does total vertical stress depend on pore pressure in the reservoir? No, because it's just the overburden. So that's going to be 0. And here we have just that variable. So derivative of PP is just going to be 1. And this is just going to be that. It's going to be a function of the Biot coefficient and a function of the Poisson ratio. And that parameter or that coefficient is called the coefficient A. And it tells you what is the variation of horizontal stress with pore pressure. Let me draw again what I showed in the previous plot. Here we're going to make a plot of total stresses as a function of pore pressure. So we'll put pore pressure over here, we'll put the total stresses over here, and let's say that we start at some pore pressure around here. And let's say that the initial vertical stress is this. We just said that the total vertical stress is not going to change with pore pressure. So this is just going to be a horizontal line. We also said that for this particular problem, it's not necessary though for what we did before, but for now, let me just put here that the initial horizontal stress is lower than the initial vertical stress, and this one, according to this equation, is going to be, let's see what is going to be. Will this A be a positive or a negative value? So alpha is positive, right? And the Poisson ratio cannot be larger than 0.5. So this has to be a positive value. So if there is a negative change in pore pressure, remember that we're going to go into this direction. If there is a negative change in pore pressure, there has to be a negative change in the total horizontal stress. So that means that this one has to go down. And the rate at which it goes down, the slope of that is that coefficient A. So the higher that coefficient, the steeper the value of, the steeper the slope of this curve. The faster S22 is going to go down. All right, let's see what are typical values now of this A. And we just said that it is a function of Poisson ratio and the Biot coefficient. So let's say for a Biot coefficient equal to 1 and a Poisson ratio equal to 0.5. What is the value of A? So Poisson ratio equal to 0.5, which is absolute maximum. Then this is going to be 0, right? So alpha is going to be 0. Okay, now let me disregard that Poisson ratio. I wanted to say Poisson ratio equal to 0. Poisson ratio is equal to 0, then and alpha is equal to 1, then coefficient A should be equal to 1. And this is just a linear equation, so this is going to be Poisson ratio equal to 0. Let's see if Poisson ratio is equal to 0.25. If Poisson ratio is equal to 0.25, then this is going to be 0.5 divided 0.75, right? And that's equal to 0.33 with alpha equal to 1. I'm sorry, to let me do this again. 0.5 divided 0.75, that will be 0.66, so 2/3. That's going to be a value over here. And the lower you go in the Poisson ratio, the lower this value of A is going to be. And the smaller the Biot coefficient, also the smaller the value of A is going to be. So this one, this is 0.67. All right. So the message here is that if you have a very small Biot coefficient, a very small Poisson ratio, that means that when you deplete, your horizontal stress is going to go down very quickly. Why? Because it's not expanding into the lateral direction, and it's not relieving any stress into the lateral direction. So it's just going to go down with the rate of pore pressure. No, it doesn't. When the Poisson ratio is equal to 0, it doesn't. It just takes all the load in vertical direction, and it doesn't expand in the perpendicular direction. The smaller the Biot coefficient, the smaller also this slope is going to be, but in general it's going to decrease with bigger Poisson ratio and with smaller Biot coefficient. So let's take, that number for a relatively high Biot coefficient and a large and a typical Poisson ratio, and let's compare it with the experimental data. And you see over here that for this particular field in the North Sea, these changes are about 0.77, 0.82. So a little bit in the range of somewhere over here. So those rocks, let me come back to here. This rock in this paper from this author, they are somewhere over here, telling us that either the Biot coefficient is low enough and the Poisson ratio is small enough to have a value over there. And that's a relatively large value of the parameter A. That, again, is going to tell you how steep the horizontal stress goes down. Can you imagine any side effect of this horizontal stress going down so quickly? Will it be bad or will it be good? Why would it be bad? Or why would it create earthquakes? Okay, well, depletion in general, it could cause earthquakes, but it's not specifically this reason. Fracking, like in which sense?
Because when there's a depleted area, the fractures that are nearby will tend to go to the lowest.
Correct. That's one of the consequences, and this is also a big problem when you have to drill a new wellbore, because if you lower the horizontal stress to values much lower to what you originally had, when you try to drill a wellbore to this location, you find that the horizontal stress or the minimum total stress now is very low. So as soon as you hit that formation, your wellbore may create a hydraulic fracture and produce low circulation. And as you say, Joseph, if you're doing hydraulic fracture and you first deplete a wellbore and then do another hydraulic fracture further away, that fracture would tend to be attracted by this place with a low horizontal stress. Remember, the hydraulic fractures always like low stress. So those are attractors for hydraulic fractures. Okay, so those are one of the consequences, but there is another consequence that it's still under discussion, but I think sometimes it can happen. And it is that if sometimes your horizontal stress goes down too quickly, if the A is too large, sometimes you can hit inside the reservoir the limit for shear failure. If instead of going this way, you go this way, and that means the horizontal stress is going down a lot quicker, then you might hit the limit for shear failure inside the reservoir. And we'll see why now, why this would happen. But for now, let's just remember that when you deplete a reservoir, the horizontal stress is going to go down, and it's going to go down at a rate proportional to the Biot coefficient and to this function of the Poisson ratio.
Quick question.
Yes?
So two comments
Yes,
limit of
correct,
the-
correct.
Okay. And second is, we talk about like doing a hydrofracturing on the old well and drill the next well. So what's the, is the distance uh, uh, impact region of this decreasing horizontal stress? Like what is normally the impact radius of the?
It depends how much you deplete.
Okay.
So far we cannot tell that, but it would depend how far your pore pressure really went down or not.
Then how can we detect it?
Detected in which sense?
Detected that we know that this low horizontal stress is caused by another well, but not just because at that location the pore pressure is not the pore pressure, the horizontal stress is low. How do you detect this confounding factor? It is caused by another a nearby well, or it's just because the horizontal stress at that location is low?
I think that's a very difficult problem. So I wouldn't know how to do that. I think sometimes you have local variation horizontal stress due to many other reasons. And on top of that, you may have this other variation due to pore pressure. But I think that I think you propose a very good point, but it's quite difficult to actually figure that out. Yes, Rodrigo.
Can we think that this effect is somehow because when you decrease the pore pressure,
Yeah.
you're kind of creating some space in such a way that the total stress is relaxing, or?
No, and that's the point in which I want to make right now. So remember, we said subsurface is very tight. It's very tight. You decrease pore pressure, and effective stress goes down, increases in vertical direction. And we're going to see is that vertical stress, horizontal effective stress, will also increase in horizontal direction. Although the total horizontal stress goes down, that doesn't mean that the effective horizontal stress goes down. The effective horizontal stress is going to go up. So let's do that. You can plot here total stress and pore pressure, and this is a very useful plot. But in terms of mechanics and better understanding of effective stresses, we want to plot effective stresses to better understand failure. That's what I mean. Where this is sigma n, this is the shear stress, and for exactly the same problem, let's say that we start with a horizontal stress sigma 22, and with a vertical stress which we said was larger, sigma 33. This is going to be our Moore circle. As we deplete, the variation of vertical effective stress is going to be as a function of pressure. Let's write this equation. So effective stress is S33 minus alpha pp. Therefore, the variation of vertical effective stress with pressure, given that this one is a constant, is just going to be alpha. So if I have a negative variation of pore pressure times a negative coefficient, that's going to be a positive number. So this means that this is going to increase. And this is going to increase an amount alpha times pore pressure. So let me write here. This is initial. This is the initial. And this is going to be the value after the change in pore pressure, in which we're saying this is a reduction of pore pressure, right? Okay, and what about the effective stress? The effective stress, we had that equation. Where is it? It is right here. That's effective stress. Our question is, what is going to be the variation of effective stress with the variation of pore pressure? And from this equation, and actually it's going to come a little bit better from here. So if I want effective stress, I just have to subtract negative, or I have to subtract alpha p. So the variation of that with subtracting also alpha p over here, since this is going to be negative alpha, and I have an alpha here, it's just going to be this coefficient minus 1, right? Or let me think again. Yes. So, okay, what I'm trying to do is I want to add an alpha pp here and an alpha pp over there. So if I take the derivative of that, what? Well, this is effective stress, right? Yeah, but S33 doesn't change, but it changes the pore pressure. Okay, so all right, that's going to be. Let me check that, okay? But I don't want to get into those equations right now. But what I have in my notes here is that this is going to be equal to alpha minus A, and that's it. Yeah. So the change in stress over here is not going to be as big as alpha, but it's going to be alpha minus all these things. Okay, so this is A, right? This is A. I think that's correct. This is A. This is alpha. And we know that vertical effective stress is going to change alpha times delta P. Effective horizontal stress is going to be alpha minus A, where we saw that A can be quite large, but still less than alpha. And what that means is that this horizontal stress is not going to increase that much, but it will increase. And the amount it increases is going to be alpha minus A delta pp, and the result of that is going to be a Moore circle which has a bigger diameter and it moves to the right. So both effective stresses are going to increase. And I'm thinking you're whispering because I'm missing a sign, maybe. I think there's a sign missing over there. And so if I have a negative change in pore pressure, I'm going to have an increase in effective stress. And this is how much this is going to increase. Both effective stresses are going to increase, vertical and horizontal. But the vertical is going to increase more than the horizontal. But the horizontal is going to increase anyways. And if you do depletion, this is going to be the result. The Moore circle is going to move to the right in terms of effective stress. And how steep this line is from the center of this circle to the center or the apex of that one, how steep it moves is going to depend on the Poisson ratio, and that's actually going to be a line which is like this. I'm not showing demonstration of this, but just believe me for now that this is going to be the result, that the smaller the Poisson ratio, the bigger is going to be this slope. And if this slope is too big, this is why we said that before, we could get sometimes to shear failure. So we know now very well that shear is going to be a function of the effective normal stress. And again, if this is too steep, could go and hit the shear failure and could cause fractures inside the reservoir. So what does that mean? Is that if we were to hit the shear failure line inside our reservoir, you will create shear fractures inside the reservoir. That's one of the consequences of this analysis. But the most important one is that effective stresses are going to increase in the vertical direction, but they are also going to increase in the horizontal direction, which also means that if you had, for example, let's make this, let's imagine that we had another wellbore over here, and we had a hydraulic fracture in this direction. As you deplete, stresses are always going to increase in the horizontal direction, and that's going to close your fractures. That's why fractures close when you deplete. And that's why also productivity decreases very quickly in fractured reservoirs, because as you lower the pore pressure, the horizontal effective stresses increase and they close the fractures. If you had a naturally fractured formation, also these natural fractures would tend to close as you deplete the reservoir. The horizontal stress will be lower, but the effective horizontal stress will always increase.
If you decrease the pore pressure, your horizontal stress, your total horizontal stress will increase.
Say again?
If pore pressure decreases, your total horizontal stress would increase, or your effective horizontal stress would increase.
Effective horizontal stress increases. Total horizontal stress decreases. And this is a huge problem now, especially for unconventionals, because as you deplete, the fractures that were originally open, they close. And they close and they lose their permeability, and the production goes down very quickly. Even sometimes if you have some propants inside of these fractures, if your effective stresses increase significantly, the propant may either get embedded into a fracture, or it could crash and become finer material that doesn't have a permeability as high as what it originally had before. So remember, always the horizontal effective stress is going to increase, the fractures are going to close. Always, in some particular cases, it may cause some shear fractures, but that's not general at all. I would say in a very small fraction. But in general, the effective stresses are going to increase in both directions. Okay, so let's come back over here, and let's say that now we don't go through the shear failure line, but we go through this line. Do you think we're going to be able to decrease pressure and with no consequences at all? What do you think is going to happen if we increase? So what we're saying here is that if we decrease the pressure, effective stresses are going to increase in both directions. And my question then is, can we increase effective stresses in both directions forever without any consequence, particularly to the reservoir?
You'll probably get more compaction, right?
More compaction, and why would that be good or bad?
You can have less porosity.
Okay.
You can lose porosity.
And then
increase the reservoir quality.
and lose porosity, and then also lose permeability.
Yeah.
So if you go too steep in this line, you hit the shear failure. If you go too long on this line without hitting shear failure, you can get to another limit over here, something which is called the compaction yield limit. And we'll talk a little bit more about that later on. But for example, for the plastic cap, if we increase too much just the normal stress without any shear, we get to this point. If we have shear plus compression, we get to this compaction yield line. And for example, this is what causes compaction bands, for those of you that are familiar with this term from geology. So at some point, also increasing effective stress in both directions too much, that's also going to have a consequence. All right, so let me do one more thing over here, and it's just to finish up with this problem. And now we're going to use the first equation. Oh no, we already used the first equation, so we'll use the third equation. So the third equation tells me that epsilon 33 is equal to, remember that this is symmetric, so it's going to be -2 Poisson ratio divided by modulus S22 minus alpha pp plus 1 over E S33 minus alpha pp. And I combine this equation with the previous equation as a function of S33. So I don't have S22 over here. And what I'm going to get, so is going to be that epsilon 33, or the variation of epsilon 33 with the variation of pore pressure is going to be equal to negative well, no, okay, wait. Let's not skip steps, because it's not going to make a lot of sense otherwise. Okay, epsilon 33 is going to be equal to 1 over E y minus 2 Poisson ratio 1 plus Poisson ratio 1 minus Poisson ratio S33 minus alpha pp. So this is just a strain as a function of total stress and pore pressure. And now what I wanted to do is the variation of strain in vertical direction due to variations in pore pressure is going to be alpha times this thing. And do you guys recognize what is this? So this is an equation we already had before. This is effective stress. And this is vertical. This is effective vertical stress, effective vertical strain for a 1D strain condition. And do you remember the name of that modulus? That was the constrained modulus, and it's a modulus I like very much. You will see that in the exam I gave you, that appears over there too, and that goes by the letter M. So,
Can you repeat that, please?
yeah, this is all this thing is the constraint modulus. And it's a relationship between strain, vertical strain, and vertical effective stress for a 1D strain condition. And directly from this equation, what I get is that the change of strain due to a change in pore pressure is going to be proportional to the Biot coefficient, inversely proportional to the constraint modulus of the material times the change in pore pressure. If I have a negative change in pore pressure, negative times negative is going to be positive. It's going to be a compression. And if you want to predict what is going to be the change in height of the reservoir, where this is the total height, simply what you have to do is just multiply the strain times the height. And this delta H is going to be this. And this is what will allow you to judge if, for example, you have problems of casing buckling. I'll tell you in a bit what that is. Subsidence, could be buckling, could be shearing. And the amount that the surface, the top of the reservoir goes down, it makes sense. It's proportional to the change of pore pressure, inversely proportional to the stiffness of the rock, and proportional to the height. The thicker the reservoir for the same strain, the bigger the displacement is going to be. Whether this goes on the surface or not, that's another problem, okay? But with this problem, assuming an infinitely long reservoir and relatively thin, this is what you would get. And this will be the value of subsidence. Are you guys familiar with subsidence? do you know cases of subsidence? Do you know one, Rodrigo? Can you tell me an example? Ecofisk, right? The paper I share with you is about Ecofisk because they had problems of significant reduction of stress and significant subsidence, so that they had to jack up their offshore platforms because they were just sinking into the water. And in that case, you know, it's this type of subsidence is not good for offshore facilities, not good for the offshore platforms. It's not good when you have to go and drill another wellbore. But sometimes you can have very serious problems of subsidence on surface too, and on onshore locations with impact to civil infrastructure. For example, in Long Beach, California, in the 30s or so, there were big issues about subsidence near Long Beach, in which you will have subsidence in the order of 10 feet. We're talking in the middle of the city. So that's a lot. Then they figured that in order to avoid subsidence and continue producing oil, you will have to maintain reservoir pressure and not to lower it too much, because otherwise the surface will just sink. And particularly for the case of Long Beach, those reservoirs are relatively shallow. That's another thing that helps subsidence to propagate to the surface. If you have a shallow formation, then the strains in the reservoir are going to propagate more easily to the surface. But also those reservoirs were relatively soft carbonates with a very thick thickness. So they were very thick reservoirs. And all of those, so soft, thick, and this one stop working. Unless I have 3 hands. No, right? So, okay. So the combination, again, of here, a thick reservoir, a soft reservoir, and huge changes in pore pressure made us subsidence quite large. All right, so I think that's everything I have for today on the theoretical part. But let me tell you that the project that you have to start working on next week is related to this. Yes, go ahead, Jack.
So you have this equation, and are you using this only as a indication, like relevance, or you actually use this equation to calculate the height of subsidence?
This equation is to calculate the deformation of a reservoir at the top of the reservoir unit.
Okay.
Whether that goes on surface or not, that depends on other things. So the second part of the project is going to be related to this problem of depletion. And you're going to have to compare these simple analytical solutions, considering that pore pressure changes everywhere the same, that it's an infinitely long reservoir, with an actual model that you're going to have to use this reservoir simulator called CMG in order to match your solution with, or the analytical solution with the numerical solution, and see how pore pressure affects that change of horizontal stress. And I just uploaded also, I think this is more or less self-explanatory, and everything you need here, you know, we come back to PQ, but you already know what that is. BHP means bottom hole pressure, and I added to a few files that are going to help you to solve that. So there is a tutorial about CMG, just CMG, another one about CMG with geomechanics, and there are 2 files that you can load to just do one simulation, make sure that everything is all right. For those of you that are not enrolled in this department, you need to send an email to John Cassibury, and the email is right here, and tell John that you need to log in into this computer lab, because we just have licenses in this lab. I'm not sure we have those in geology. I don't think so. But just send an email to John, and he'll add you to the list of users, so you can log in the computers here in the 2nd floor and run the simulations.
What's the name of the lab?
It's a computer lab. It's right above this room, somewhere over here. Okay? All right. Any questions? No? Well, then we'll finish here, and I'll see you on Monday.